everyone, welcome to the next session of fluid mechanics. In this session, we will be discussing about another property of fluid which is a very important one, that is viscosity. Viscosity is one of the reasons why we study fluid mechanics, apart from the other reason being the geometry. If there is no viscosity of a fluid, then a fluid would continue to flow forever in this universe. It is something like friction that you study in engineering mechanics. Let's define it. It is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. So let's talk about a fixed surface here, say your table, on which there is some amount of water that falls. If you tilt this table, you will see that the layers of water are flowing away. But one layer of water will obviously keep sticking to the surface. That is because the first layer, which is closest to the surface, will take the velocity of the surface itself. That is 0. So at this surface, the velocity is 0, and as you move ahead or you move upwards, you will see that these layers are going to have different velocities. That is because here the viscosity is going to be more. That is because of the shear stress that is applied by these layers. One layer applies shear stress on the other. Now it starts from the surface, that is the stable surface. So the stable surface on which the first layer is lying will try to move in this direction, but the table will try to pull the layer backwards. So this is shear applied from below on this layer. Now this layer will apply shear stress on the layer above it and try to pull it behind, whereas it will try to move ahead because of the velocity or the tilting of the table, as I can say. Now similarly, each and every layer will keep on applying shear stress up to the last layer, that is the topmost layer, which will have minimum shear stress applied on it, and that is why it will have more velocity to move forward. That is the resistance which is written over here. Resistance to the movement will be least for the topmost layer. So suppose if I apply velocity u, it will start moving with the velocity, and slowly the velocity will reduce up to the last layer where the shear stress is more, and here the velocity will be 0. So this is the basic concept of what is viscosity. Now when you talk about a fluid, for example water, there will be a particular value of viscosity. When you talk about honey, there will be a different value of viscosity. Now just imagine that on a table you have some water lying, and on the other side of the table, say there is some honey lying over here. Let's tilt both the table and see. You will see that water moves very easily. When I tilt, I mean I'm giving some velocity because it will be coming under the action of gravity. So it will start getting pulled and it will start moving downwards. So in short, I can say I'm giving some velocity to this kind of a fluid. So here you will see that the layers will start moving faster for water. Whereas when you talk about honey, you will see that these layers move slowly, and also the viscosity is more. Now when you talk about viscosity, I would say how thick or thin the fluid is. If the fluid is little thinner, then the liquid will move faster. But when you talk about honey, the liquid is little bit more thick. I am not saying dense. Density is different. I am saying it is thick. So it is going to move slowly. So when you talk about viscosity, you should essentially think in terms of the liquid being either thick or thin. So that's the basic definition, and these are some examples of viscosity. Now let's take up an example of a layer. Say I have a fixed layer. This direction will indicate my velocity u, and this is the y direction. Say in this direction I am talking about two layers. This layer below has velocity u, and the layer above has velocity u plus du. Obviously it will be little more. You can say that the velocity profile, because of these layers that I just discussed, will be something like this. It's a parabolic shape. This is called as velocity profile. The shape of your velocity change in the y direction. So this change in velocity is du, as you can see, and these two layers that I'm talking about, say they are placed at a gap of dy. Now it is observed experimentally that the shear stress that is applied by these layers on each other is directly proportional to the velocity gradient. This du by dy is called as velocity gradient, because you can see over here this is nothing but du, that is change in velocity from one layer to another. So I can say that it is change in velocity with respect to the direction, or the change in direction. That's what you can say. So this is called as velocity gradient. Also this term du by dy is called as rate of shear strain. The reason being, let's talk about the unit now. When you look at the unit, this du by dy has the unit of meters per second upon meter. Du is change of velocity. Velocity is always in meters per second, and dy is the direction. So let me say it is in meter. Now let's rearrange these terms and let me write this as meters per meter upon second. Just rearranging these terms. Meter per meter is going to show nothing but your change in dimension over another dimension, which is essentially the topic of strain. And when I say per unit time, obviously it is talking about the rate, that is the change of something. So what I am showing here is the rate of shear strain. Now why have I attached the term shear? Because there is a shear stress acting on the body. So obviously the strain has to be called as shear strain. So from the units you come to know this name. Now here also it is very simple. It is velocity gradient. This also can be defined in terms of unit du by dy. Again the unit is meters per second upon meter. You can see this is change of velocity with respect to the direction. So this is velocity gradient. So these are the two names which can be even thought of by using the units. Now, when I say in mathematics one term is proportional to the other, I can always remove the proportionality sign. So I can say therefore tau is equal to mu du by dy. This mu is nothing but constant of proportionality according to mathematics. Also, we can call this as coefficient of viscosity. Or this can be called as dynamic viscosity. Dynamic viscosity is the name, or it is simply called as viscosity. That is mu. Now let's talk about the unit of this term mu. For that I am going to shift mu on one side and rest of the terms on the other side. So I'll have therefore mu is equal to tau upon du by dy. Let's talk about the unit of these terms. For tau, the unit is Newton per meter square. Here, this is meters per second. And this is 1 upon another term. So this unit will definitely go into the numerator as meter. So this meter gets cancelled and the unit remains as Newton second per meter square. This is the SI unit of viscosity. Now let's talk about the CGS unit. I can convert 1 Newton second per meter square to dyne second per centimeter square. We know 1 Newton is 10 raised to 5. Dyne second is not getting converted, so it is as it is. Meter square to centimeter square. We know 1 meter is 100 centimeter, or it is 10 raised to 2 centimeter. So I can say 1 meter square will become 10 raised to 2 centimeter square. This 2 into 2 is 4. So I have 1 meter square is 10 raised to 4 centimeter square. So let's substitute here. This gets cancelled and what remains is just 10 dyne second per centimeter square. This term dyne second per centimeter square has been labeled as poise. So this is nothing but 10 poise, or you can write the entire term. Now since we are writing the name of a scientist, we need to write this as small p, and if you want to write this as a unit term, you can write it as capital P. For example, if you are writing 10 Newton, you write it this way, and if you are writing the name of the scientist completely, this is 10 Newton. Similarly here, this is 10 poise. So I have 1 Newton second per meter square is 10 poise. Or you can say 1 poise is 1 upon 10 Newton second per meter square. As you require it for the numericals, you can shift it. Now another conversion that you need to remember is 1 centipoise, which can be written as Cp is 1 upon 100 poise. So this is another conversion to be remembered for solving of numericals, wherein the data is given either in terms of centipoise, poise, or it could be in directly Newton second per meter square. So we just need to convert into one type of unit system and solve the numerical. So for that, this will be required. And one note that you can keep with you is the value of mu for water. Again, a standard fluid at 20 degrees Celsius is 0.01 poise, or it is 1 centipoise. Now why do we say at 20 degrees Celsius, though the temperature at the place that you might be right now will not be always 20 degrees Celsius. So this is something which is called as STP, standard temperature and pressure. There is also something which is called as NTP, normal temperature and pressure. Normal is, for example, right now I am sitting in a country wherein the temperature is say 30 degrees Celsius. So for me, normal temperature is 30 degrees Celsius. But suppose right now if you are sitting in a country wherein the temperature is say minus 3 degrees Celsius, for you that is your normal temperature. But that does not mean that I have to always define this as a standard value, because it will vary from time to time. So we cannot use NTP as a standard, because the value of temperature and pressure, depending on altitude, your pressure will change at which altitude on earth you are sitting. So obviously NTP is something on which we do not define the values. We define based on STP, that is a standard temperature and pressure is taken. At that temperature and pressure, we are defining the values and accordingly we are using it worldwide. So this is all about the topic of dynamic viscosity. There is another term for viscosity that is called as kinematic viscosity. This is very important. When you talk about dynamic viscosity, you mean to say that your fluid is in motion, because that's where I started by drawing this kind of a diagram, explaining you about water, honey, by saying that the table is tilted and hence the fluid starts moving. So I was talking about something dynamic. The fluid was in motion. But when I talk about kinematic, it is about a fluid which is in motion without considering the forces acting on it. So it is defined as a ratio between dynamic viscosity and density of fluid. So this is the definition: viscosity upon density. Viscosity is essentially used for the term dynamic viscosity directly. Technically, there is no requirement of saying that it is dynamic viscosity. But yes, when you talk about kinematic viscosity, you need to mention the term kinematic in front of it. Otherwise, people will understand that you are saying about dynamic viscosity. It is denoted by the Greek symbol nu. This is the N for Greek symbol. So I am writing nu is mu upon rho. This is the formula for kinematic viscosity. Now let's talk about unit of this term nu. This will be unit of mu upon unit of rho. We just discussed about the unit of mu, that was Newton second per meter square, and the unit of rho is kg per meter cube. So meter cube goes to the numerator. This is meter square and this is meter cube, so 1 meter remains. And this Newton also can be further written as kg meters per second square. 1 second remains, 1 meter remains, and this is kg. So kg gets cancelled, 1 second remains here, and this now becomes meter square per second, which is the unit for the term nu. This is going to be the MKs or the SI unit. Let's convert this into the CGS unit system. 1 meter square per second can be converted into centimeter square per second. We just discussed 1 meter square was 10 raised to 4 centimeter square. So I'll directly write here. This centimeter square per second has been renamed over a physicist, that is Stokes. Hence this becomes 10 raised to 4 Stokes. If you want, you can also write this as 1 Stokes is 10 raised to minus 4 meter square per second. The reason for discussing about this term Stokes is in the handbook or the data book, as you can call it, you will find the value of viscosity of oil in terms of poise and Stokes. That's a way of representing. Hence, we should know about these conversions. And one more conversion is 1 centi-Stokes is 1 upon 100 Stokes. Having said this, we will discuss little bit in detail about this unit that we just found, meter square per second. When you look at this unit, you will see that meter square is the unit of area and second is the unit of time. So looking at this way of studying, this is called as a dimensional analysis, wherein you analyze the units. So I am analyzing that viscosity actually means it is talking about area per unit time. Now area cannot be directly written that way. So I can say that amount of area that a fluid occupies per unit time is my kinematic viscosity. So that is why you should understand that dynamic viscosity is talking about the fluid in motion. But yes, there is a term force associated over there because the unit contains the term Newton. So force comes into picture. And when I talk about kinematic, the fluid is in motion, definitely. But you would say that there is no force coming into picture. Generally, we use the term kinematic when we say that there is no force on the body, but the fluid is in motion. So here also the same concept can be applied. Here there is another way of representing the term nu, that is the area occupied per unit time. And we are not talking about the term force over here. So this is a physical significance of kinematic and dynamic viscosity, which I just explained to you. So with this I end the session. I hope you have understood the concept of viscosity. So see you in the next session. Thank you.